Hello viewers, welcome back to the course on matrix computation and its application. So, today we are going to discuss the next thing, that is basis and dimension, and this is lecture number 13. So, let us start with this one. So, now we are going to define the terms basis and dimension. So, what is the meaning of that? Now, suppose I have vector space V and a subset B of the vector space V is said to be a basis for the vector space V if the first one is that B is linearly independent, because this is a subset and it contains the vector. So, the B is linearly independent, and the second one is that the B spans V. It means that the span of B is equal to the complete V. So, in that case we say that this B is a basis, and here we can write also we can say that B generates V. So, the set B is called basis of the vector space V, and number of elements in B. So, the number of elements in B, whatever the number of element is there, is called the dimension of vector space V. So, two things we have to perform. We have to check it is linearly independent or not, and second one, it should span this one. So, let us do this one. So, let us take one example. So, suppose I just take vector space as V3, that we are taking as R3. Okay. So, in this case I just take a set B is made up of, suppose I take 1 1 0. So, just 1 1 0 1 0 1, and then I take 0 1 1. So, I just take 3 elements in B. Now, we want to check whether B is a basis or not. So, this one we want to check. So, the first thing is that check first B is Li. So, this one we have to check. Now, this can be done with the help of the matrix. So, because we know that when we write the linear combination, this can be written as 1 1 0 1 0 1 0 1 1. So, we come across this matrix. So, whatever the vectors are there, we will put it as a column vector in the matrix A, and then I will reduce this matrix to the echelon form. So, I will apply, first I will make this 0. So, I will apply minus R1 plus R2. So, this will be 1 1 0 0, and it is minus 1 1 0 1 1, and then I will take R2 plus R3. So, from here I will get 1 1 0 0 minus 1 1, and then 0, adding here it becomes 0, it becomes 2. So, from here I can say that the rank of A is 3. So, it is invertible matrix. So, from here I can say that set B is linearly independent. So, that is there, that the B is a linearly independent set. So, now from here this one, now I want to check the second property such that B spans V. So, this one I want to check. Now, what I do is that let we take a vector x1, x2, x3 belongs to V. Then we just try to write x1, x2, x3 as a linear combination of, maybe I can take this as A and taking the 1 1 0 plus B 1 0 1 plus C 0 1 1. And now from here I can write this as, so from here you know that you get a matrix 1 1 0 1 0 1 0 1 1 A B C, and it is x1 x2 x3. So, this become matrix A into some vector, maybe I call it x is equal to B. So, this is my B. So, this is my system. Now, I want to solve this system. So, we know that how to solve this one, because it is a 3 by 3 matrix. So, we can find our inverse also, but generally we go by writing reducing this into the echelon form. So, now from here I can write its augmented matrix. So, that is 1 1 0 1 0 1 0 1 1 x1 x2 x3. So, this is my augmented matrix, and then I will apply this to make it row echelon form, as we have done in the checking that this is linearly independent or not. So, I have just taken minus R1 and adding to R2. So, it is 1 1 0 x1. Now, it is becoming 0 because I am multiplying by minus 1 and adding. So, it is 0. Now, I am multiplying minus 1, and so it is minus 1, it is 1 and minus 1. So, it will become minus x1 plus x2 and then x3 0 1 1. Then again I am applying this because I want to make this element 0. So, I am applying R2 plus R3. So, I will get 1 1 0 0 minus 1 1 0 0 2. So, it become x1 minus x1 plus x2, and I am adding here now. So, it become minus x1 plus x2 plus x3, and now it is a echelon form. So, from here using this one we can say that 2c is equal to minus x1 plus x2 plus x3. So, my c will be minus x1 plus x2 plus x3 by 2. So, this is the c I got. Now, from the second equation I will get minus b plus c is equal to minus x1 plus x2. So, from here my b will become so, I take the c here. So, that will become x1 minus x2 plus C. So, this one can be written as. So, I can write it as x 1 minus x 2 plus, so C is this one, minus x 1 plus x 2 x 3 by 2, and from here I can write 2 x 1 minus x 1. So, it will be x 1 minus 2 x 2 plus x 2. So, minus x 2 plus x 3 by 2. So, this is my B, and from the first equation I get A plus B is equal to x 1. So, my A will be x 1 minus B. So, minus of this one, so that gives me 2 x 1 minus x 1. So, x 1 plus x 2 minus x 3 by 2. So, that is my A. Now, you can write down that from here we can write. So, I can write from here that my x 1, x 2, x 3 can be written as, so A is this one. So, it can be written as x 1 plus x 2 minus x 3 by 2 1 1 0. B is this one, x 1 minus x 2 x 3 by 2, it is 1 0 1 and plus minus x 1 plus x 2 plus x 3 by 2 0 1 1. So, this can be written like this one. So, from here you can see that for any value of this one I can get the linear combination. You just give me the vector from any vector from V3, and then correspondingly this coefficient can be found. So, from here I can say that, so from here for any x 1, x 2, x 3 belongs to V3, we can find the coefficients A, B, C. So, from here I have taken any element and that can be written a linear combination of this one. So, from here I can say that the V3 is written, can be written as the span of the vectors, span of the, so I will B. So, I can write this here. So, this is equal to the span B. So, it is spanning V3 and the B is linearly independent. So, from here I can say that B is a basis of V3. Also, the number of elements in basis V3 is 3, which implies that V3 is 3 dimensional. So, it is a 3 dimensional space V3, and that we already know because V3 is equal to R3. So, this way we can find that it is a basis for V3. Now, if I change the elements, we can get the another basis. So, that is why it is only I am writing a basis. Now, there is a very important theorem regarding this basis, because here what will happen if I say that the set B is not linearly independent, but still it is spanning the set. Then what you can say about the number of elements in the basis or number of element in that space. So, for this one there is a very important theorem. So, that theorem gives the relation between the spanning set and the linearly independent set, number of elements in the linearly independent set. So, this theorem says that in a vector space V, if V1, V2 up to Vn spans V, okay. So, it spans V, and if I take a set S that contains the element W1, W2, Wm, and this is if S is linearly independent, containing the m elements and linearly independent, then it says that m is less than equal to n. Okay, so, it says that this m will be always less than equal to n. In this case, this is the spanning set. It need not be a basis, but only condition is that it spans V, that is it. Okay, so, in this case we can also say that we cannot have more linearly independent vectors than the number of elements in a set of generators or in the set of span. Like here we have a n number of elements in this generator, because it spans V, it generates V. Then we can say that if we have a set of linearly independent vectors, then m cannot be greater than n. So, this is the way we are defined. So, here it is spanning basically. So, proof. Now, it is given to me. So, that is just it is given. Now, given the span of V1, V2, Vn, that is equal to V. Okay. So, that is given to me. Now, since W1, W2 or Wm also belongs to V, then for then I can write then each of Wi can be written as linear combination of V1, V2 up to Vn, that we can write. Okay? So, that is why we are writing like this one. So, for example, so then for I just to take Wm. So, for Wm we can write Wm as let I take A1 V1 plus A2 V2 up to AN Vn. I am writing like this one because Wm belongs to V and V is completely spanned by this one. It means I can write like this one. So, from here I make a vector set S1. So, S1 I will take first element Wm and then I will write V1 V2 up to Vn. So, definitely it is linearly dependent because one vector is a linear combination of the other vectors. So, definitely this is linearly dependent and containing n plus 1 elements. So, that is there. Now, what we are going to do is now using previous theorem. So, we can find a vector say Vi such that Vi belongs to the span of Wm V1 V2 Vi minus 1, as we have seen in the previous theorems, that we start with the first element and then keep going up till we get a vector which is a linear combination of the previous vectors. So, this theorem we are using here. Okay. Then discard all such vectors. At least one vector will be there which is a linear combination of the previous one, we remove that one and then we will continuing for the whole set and then we remove all the vectors which are making this linearly dependent. So, we discard all such vectors and we call it S1 dash. So, S1 dash is Wm V1 V2 Vi minus 1 Vi plus 1 and suppose going like this one. So, definitely this is linearly independent. So, this is linearly independent. Okay, so, we are done till here. Now, again we choose Wm minus 1. So, I can write and also, so this one is also S1 dash span that is same as S1, because this is my S1 and I have removed the linear dependent vector from here. So, span of S1 dash is equal to span of S1. So, this is there and also the span of S1 is basically the span of V. And that is span equal to V completely, because S1 is just the putting one element which is linear dependent. Now, so we follow the same procedure that is I take W m minus 1 as a linear combination of like this one A 1 W m plus A 2 V 1 up to this one. Suppose last element is coming still n, so we will take this one. Or I can say that we can write W m minus 1 belongs to the span S 1. We can write, no problem. So, now I write a set S 2 the same way, writing W m minus 1, W m V 1 V 2 this one, whatever the elements remaining here. So, out of this one I am collecting this up to V n, and it, so this is again the linearly dependent. So, if it is linearly dependent, then the same procedure can be followed, and I can write S 2 dash which contains the elements W m minus 1, maybe W m V 1 and so on, such that this is Li. The same procedure we have followed, removing the linearly dependent vectors. Okay, so this way we can follow maximum up to m times, because there is m number of elements involved, because S, because this set I am taking S contains m vectors. So, I can follow this only. So, it can be only m times, and definitely the W m, the W i's cannot be moved, because W I are linearly independent, only V i's will be removed. So, that should be there, that only we can remove the V i's, cannot be removed the W i's. And W i's cannot be discarded because of linearly independent, which implies every time V I is discarded. So, every time V I is discarded. So, from here I can say that if I follow this one, then definitely m will be less than equal to n, because start with the n elements in that set and then adding one W m, it become n plus 1 elements, and then we start removing the elements to make it linearly independent. So, and then again we are putting one element and discarding the other elements. So, definitely in the end we are left with the W m elements, or this is the maximum we can go. Even the before of that one also it may happen that all the V i's will be removed. So, from here that the m is definitely will be less than equal to n. Otherwise, the set W 1, W 2 up to W m becomes linearly dependent, which is a contradiction, because we have assumed that this W I 1, W 2 up to W m is linearly independent. Okay, so, after once we reach this one and all the V i's as removed, then it becomes linearly independent, we cannot go after that. So, in this case definitely the m will be less than equal to n. and so we able to finish this one. So, for example, just now we have seen in the previous examples that is that the set I have taken B 1 1 0 1 0 1 and 0 1 1. So, it spans whole V3. Forget about that whether it is a linearly independent or not, but definitely it spans V3. Now, suppose I take the set S which contains any 4 elements. Let us take the set S which contains 4 elements. Just I take, maybe I can take the same element 1 1 0 0 1 0 and suppose I take 0 0 1. So, 4 element I am taking. Then definitely it will be linearly dependent, because we are going to have a matrix 1 1 0 1. Oh, so I have taken the same element. So, 1 0 1, then I am taking 0 1 0 0 0 1. Suppose I have taken these elements. So, this is 3 cross 4. So, in this case I know that the rank of this matrix A, suppose I take it A, is always less than equal to 3. So, definitely it cannot be a non-singular matrix. So, rank is always less than equal to 3 and the number of variable will be 4. So, infinite many solutions, and from there we know that this will be linearly dependent. So, using this one I can say that set S containing 4 elements, 4 or more, so from here I can say that any set S containing 4 or more than 4 is always linearly dependent. Okay, so it will always linearly dependent, and 3 we know that it can be shown that it will be linearly independent, or 2 can be linearly independent, but more than 4, more than 3 is always going to be linearly dependent. So, that is the one of the way we can use the previous theorem. So, let us stop here. So, let us stop here. So, today we have discussed some other properties about the vector spaces. We have defined the basis, the dimension, and in the next lecture we are going to be continue from this one. So, thanks for watching. Thanks very much.